Over at Columbia Journalism School, we're conducting a variety of research projects to better understand the ways in which AI can help to produce fact-based news and to combat the ways in which it can flood the ecosystem with misinformation, propaganda, and slop. Engineers, scientists, and policymakers that you're going to hear from today are among those who will help shape how the future of the next wave of artificial intelligence tools will shape our planet. You will hear from people like Professor Smaranda Muresan, who, for instance, focuses her work on ensuring that the development of AI remains aligned with human values. And you'll hear about efforts from folks like David Sandalow, another speaker today who's working to help ensure that the negative environmental impact of the introduction of new technologies are minimized, and in fact that these technologies can be used proactively towards productivity of solar power plants, efficiency of buildings, and things like that. You'll hear from folks like Matei Ciocarlie on ways that AI can be used by robots to operate in the physical world and hopefully improve it. So regardless of what your role is, whether you are an engineer, a scientist, a journalist, a policymaker, a business person, and especially if you are a student, I hope that these talks and the following conversation will inspire you to think about what your role will be in the development of these technologies, how the intentional decisions that you make within the context of within your context in your industry will shape the future that we all have to live in, and how making a different decision could materially alter that future for better or for worse, hopefully for the better. And so without further ado, I'd like to welcome our speakers for today. We'll start with Professor Vishal Misra. I'll do a quick intro.
Oh, sure.
Professor Misra is a professor in computer science and electrical engineering departments and is the vice dean of computing and AI at Columbia Engineering. His research focuses on mathematical modeling of systems. He developed a stochastic differential equation model for TCP, applying classic control theory to design congestion control mechanisms that have become part of a global standard that's in all of our cable modems. He's also the co-founder of Cricinfo, now the world's most popular sports portal, which was acquired by ESPN. He has contributed to the public discourse around net neutrality. Strong regulations enacted by the Canadian and Indian governments align with the definition of net neutrality that he proposed. He's a distinguished alumnus from IIT Bombay, where he got his BTech, and got his MS and PhD at University of Massachusetts at Amherst, where he's also a distinguished alumnus. Please join me in welcoming Professor Vishal Misra.
Thank you for the introduction. Thank you for organizing this panel, and thank you all for coming here. Good morning. So I'm going to talk about language models, both small and large. And the title of my talk is The Secret Behind LLM Intelligence, Good Old Bayes in Disguise. So I'll first start with what does Bayesian really mean? So just a quick introduction. So the idea behind Bayesian is, suppose your initial belief that it's going to rain today is 10%. That's a probability in your head. The left, the squiggly thing is your brain. Now that I've told you that it's your brain, your belief has gone up from 10% or whatever. But you walk out and you see dark clouds appearing. When you see that, then your probability that it's going to rain in your brain changes from, let's say, 10 to 95%. You're almost certain that it's going to rain. So Bayesian thinking basically is updating beliefs when new evidence arrives. So you start with what you know, which is your prior, and then you'll adjust based on new evidence. And the strength of the adjustment depends on how convincing the evidence is. So that's what Bayesian thinking is. And then rest of the talk, I'll tell you how that relates to large language models. So the LLM revolution is just about predicting the next word. How do LLMs work? Well, the training objective when you train these LLMs is to predict the next word in a sequence. So when you give the LLM a sequence like the cat sat on the, then what the LLM is trained to do is generate this probability distribution where the probability of the next word is highest for, let's say, mat. The cat sat on the mat. The cat sat on the couch. And very low probabilities for the cat sat on the courage. Maybe somebody wrote a poem, whatever. But what the LLMs do is they generate this distribution based on what the prompt is. And then from this distribution, they'll sample the next word. And then that's how completion happens. That's how LLMs generate text. And they implicitly learn things like world grammar, because they realize during training that I see cat sat a lot more than cat sats. So the probability of cat sat is much higher than cat sats. So explicitly they're not told this is grammar, but they implicitly learn. Similarly, they get world knowledge. The probability of cat sat on math is much higher than probability of whale sat on math. Even arithmetic, they see samples of correct equations during training, and from that they sort of implicitly learn arithmetic. Otherwise, they don't know that 2 plus 2 is 4. They don't even know 2 is a number. It's just some embedding in their architecture. So the shocking secret is all that AI brilliance just comes from this optimization metric. Predict the next word. That's all they are trained to do, and everything that you're so shocked and amazed by comes from that. And so what I'll do quickly is try to explain how that happens. So in context learning is a new paradigm that these LLMs, when they appeared, they introduced. So there's a thing called zero-shot learning and something called few-shot learning. So in the zero-shot learning, models solve the task with only a description, do something to X or Y. In few-shot learning, the model will learn from examples in the prompt. For instance, you can show the model what is sentiment analysis. So in your prompt, you say, what is the sentiment of this review? I like the movie, positive. What is the sentiment of this review? Horrible movie, negative. Then you say, what is the sentiment of this review? This movie is boring. From these examples, the LLM learns, okay, you want me to do sentiment analysis, and the keywords that you're using are positive and negative, so it'll respond with negative. Movie is boring, it figures out that it's a negative review. But the thing is, it goes beyond standard tasks. LLMs, the sentiment analysis review, I think is a standard task. LLMs can just learn from training data. But they go beyond standard tasks. They can learn completely new tasks with arbitrary labels. So in this example, we could have said foo and bar instead of positive and negative, and the LLMs will pick it up. And this is really the sort of game changer with LLMs. They do real-time learning as opposed to offline learning. So the old paradigm of machine learning models or even language models was it required hours, days, even months of training to get knowledge to a certain level to respond to prompts. It was resource intensive. It requires specialized hardware. We all know what NVIDIA's stock price is, and this training is slow. But with in-context learning, this new approach, there is no retraining required of the model. The model picks up from examples new things, and it sort of works with the existing trained model, works with the existing infrastructure, and in microseconds or seconds picks up new tricks. It learns to do new things. So it has changed the whole time scale of learning from a slow process taking hours, weeks, months to real time. And that's really the game changer. So what it does is, it's not just few short examples, but the model continuously adapts to the prompt. And it sort of understands the user context, the style. It has a human-like ability to understand implicit context, where you don't say explicitly something, but it'll pick up from what you're saying by adjusting those probabilities that I spoke about earlier. And this learning happens during the conversation. There's no retraining involved. From the prompt, it learns what you want. So because of this process, things like instruction following happens. So these models can understand complex multi-step tasks. We all use these LLMs. We tell them do this, do that. How is that happening? It's because of this Bayesian adaptation. It'll adapt to specific formats, requirements. You can even show a completely new format and it'll learn. It also shifts the tone, formality, and style as needed. it maintains conversation coherence, and it sort of tracks the context as it evolves during a conversation. We have all experienced this, starting with the first version to ChatGPT to all the LLMs that we see now. So at a macro level, what you can imagine is these LLMs are translating a prompt to that distribution. You know what I said, the cat sat on the, and there's a distribution with mat, couch, courage, the. So at an abstract level, you can think that it's a giant matrix where every row is a different prompt and the columns correspond to the next word probabilities. So each column is like a word, and given a prompt, you have this distribution of probabilities. But it's impossible to store this entire matrix completely. If we just take GPT-4, the kind of parameters it has, the kind of context length it can store, the number of rows required to represent this matrix are more atoms than in the observable universe, 10 to the power 80. You cannot possibly store it, right? So what these models do is, through this process of training and Bayesian retrieval, they learn how to approximate this matrix as best as they can. So the task is to represent this completely. You cannot do that, possibly. It's impossible to do that. But what these LLMs learn to do, and some do it better than the others, is approximate it using this process of Bayesian learning. So what is LLM posterior updates? It's shifting distributions in real time. So suppose the LLM was trained and the training stopped a year ago. So the probability of who is the current US president, the probability would look something like that, where Biden would be the highest, Harris and Trump would be the lowest, because that's what the LLM was trained on. Now, if in the prompt you say, as of January 2025, Donald Trump was inaugurated as a 47th president, then what happens is that this probability shifts from Biden being at the peak and Trump and Harris being low to Trump being highest. Because you have given this new information in the prompt, the LLM has adapted. Next time it has to say something about the president, the probability would be high of Trump. Now, if I was into gallows humor, I could have used a different precedent and much more local examples, but I'm not going to go there. Angela is sitting there, she's suffered enough. So how does this happen? So what happens is, during training, I'm not going to get into the details of this architecture, but what happens in the training, when you give this model a prompt and ask it to complete, if it ignores information in the prompt that was important for completion, then it gets a big loss, and the training process makes sure that the model learns to pay attention to the prompt. So during the prompt, it has been trained on something, now you give it something new, but in the prompt there was something important that it had to use to predict the next token. When it fails to do that, the training process signals, no, you shouldn't be doing that, pay attention to this. So during this training process, it learns to pay attention to the prompt. Now the thing is, this is not explicitly programmed. This just arises from optimization and the right kind of training data. You need training data when the prompt is important. So we have shown that if you have training data where the prompt is not important, the LLMs do not pick up this ability. So it's not simply the architecture, but also the right training data. So the aha moment is when LLMs learn to make a decision. So in the prompt, before you present some key evidence, there are many possible answers. The distribution that I showed earlier, it could be very spread out, lots of possible choices. But if you give key evidence, then the probability sort of starts collapsing to one possible next token. The model becomes more and more confident and says, oh no, this has to be the next one. So this is why things like chain of thought prompting work, where you ask the model to solve something using chain of thought. So, step one is understand the problem statement, break it down into sub-problems, apply specific operations. and synthesize the results into the final answer. At each step, the model will recall something that it has seen in the training, which is similar to those steps. And then using the Bayesian process, it'll adapt the example that it knew from the new parameters that you have given to the problem. And it becomes more and more confident at each step. So that's why, things like chain of thought become much more accurate than asking the model to solve something right away. So there are lots of implications and next steps of thinking these LLMs in this sort of Bayesian paradigm. You can do better prompt engineering. I don't like the term, but that's what everyone uses. You can develop better prompts. You can control hallucinations. So hallucinations happens when you have lots of different choices to go to the next word, and the model might pick the wrong one. The way to prevent it is to narrow that distribution, make the model more confident where to go. There's something called retrieval augmented generation by strategically inserting evidence. So again, this Bayesian way of thinking helps with that. And you can have different kind of architectures, explicitly exploiting these Bayesian properties. So we have actually shown that a very small model with just 2 million parameters, GPT-4 is supposed to have 1 trillion parameters. With just 2 million parameters, we can show that the model learns to do in-context learning for a very focused problem. So this is a way to go from large language models to small language models. So now I'm going to stop. I'm getting the signal. I'm sure there will be questions during the panel, so we'll save the questions for that. Here's some work. If you have any offline questions, you can send me email or contact me. I'll stop here.
Thank you very much. Our next speaker is Professor Smaranda Muresan, who is an associate professor in the Department of Computer Science at Barnard College, is affiliate faculty in the Department of Computer Science at Columbia, a member of the Data Science Institute, and an Amazon scholar. Her work is focused on human-centric natural language processing for social good and responsible computing. She developed theory-guided and knowledge-aware models for understanding and generating language in context. Professor Muresan has worked on topics ranging from argument mining and generation to fact-checking and misinformation detection, figurative language understanding and generation, like identifying sarcasm, metaphors, idioms, language and vision, and multilingual language processing for low-resource languages. Her work has applications to computational social science, education, and public health. She is also interested in explainable models, human-AI collaboration frameworks, and aligning AI systems with human values. She got her BS in computer science from the Technical University of Cluj-Napoca in Romania and got her MS and PhD in computer science here at Columbia University. Please join me in welcoming Professor Smaranda Muresan.
Thank you. Thank you, everyone. I'm very happy to be here to talk about our work on natural language processing for social good, taking a human-centric approach. So when we talk about NLP for social good, I'm going to give some example of the work that we are doing. In journalism, for example, we are looking at detecting misinformation. When we have an article or a piece of information, what do we need to fact check? Why do we want to fact check that piece of information, and how we go about doing that? And one of the important issues, besides just saying that something is true or false, we want to identify misleading content, fallacy, something that it's half true, half false. Another area we're working on is public health, and this is a collaboration with the Office of the City Medical Examiner in New York City, as well as School of Social Work and the Friends Research Institute, on predicting opioid overdose deaths from investigative reports. And here what we want the model to do is not only to make prediction, but also to provide clear evidence from the document why we make that predictions. Another application is education. So we want, for example, we are working on developing these NLP technologies to improve students' writing skills. For example, using argumentative writing, can students identify what's the main claim of an article? What is the evidence? What are the premises? What support what type of evidence? And providing also alternative, for example, counter arguments to a particular topic. The other area we are looking at is improving creative writing skills and using these creative writing assistants for students. And here one question we are looking at is where technology stands. Is the technology really good at helping students, for example, in the creative writing? And I'm going to come back to this at the end in the solution we propose. And then last but not least, I would call it NLP for all. A lot of the technology is developing, for example, for English or for US-centric or Western-centric views. And we want to look at developing technologies for low-resource languages, languages that have, for example, much more complex linguistic properties like morphological complexity, like polysynthetic languages, and also equipping these models with information about cross-cultural understanding, like norm discovery. Given a particular situation, there are norms in English, but they are different in other cultures, like, for example, in Chinese. How can we discover this from text, from multilingual text, from multimodal, for example, discussion, and then ultimately, how can we equip the model to have this information when they make decisions? So some of the challenges there are, especially in the era of large language model, is reasoning capability, right? So can we make this model reason better about the world? High quality data sets, which I think are very, very important, not only to build the model, but also to evaluate this model, particularly smaller models, on user relevant tasks, which I think it's, again, one of the challenges. And then last but not least, really evaluation protocols. How can we value and judge the quality of the model output as well as the quality of the model that are used as evaluators? So think about creative writing. We are using this technology to assess student writing. Is it good or not? Are they actually good to do this job? So this is another challenge we want to address. So the technical solution I'm proposing and my group is working on is to use these smaller models, starting with this larger model, but really augmenting them with knowledge that we already have. For example, linguistic knowledge. We know the typology of languages. Can we use this information as priors to the models? Or domain knowledge. For example, in the public health, there is a lot of domain knowledge already existing in ontology, on knowledge basis. Can we use that to augment the models? And then ultimately social cultural norms that we are discovering and then improving the models on that. The other part is a human-AI collaboration frameworks. I think that's very important, both to generate high-quality data sets, but also ultimately to help improve the model. And I'm going to give an example of using in-context learning, the way Vishal mentioned, with expert feedback, then using model distillation, which means taking a larger model and train smaller model to do the same task, explanation generation as well, and then ultimately help humans solve tasks. So let me give you here just one example on this human-AI collaboration and on a particular application, which is multilingual, multimodal social norm discovery. So here what we do, we start with a large language and vision model, for example, and we look at videos in particular. I know it's very small to see, but basically what we want to discover is the context of the conversation. So for example, discussion between friends. What is the particular norm that we have? So if we have, for example, a request for information, is this, the norm should be, you have to ask politely this question. Is this a norm violation or a norm adherence in this particular scene? And what is the verbal evidence and the non-verbal evidence given in this particular, let's say, conversation? And then what we have is that we have actually experts, let's say people that are aware of the culture in a specific, like we are looking at English, Russian, and Chinese, and they can actually change the model's output. For example, let's say they didn't identify the right norm or the right evidence, and then use in-context learning afterwards with feedback from the human to improve further the models, and then using them to label a larger amount of data, which is high quality because of this expert in the loop, and then we use them to train explainable smaller model to do the same task. And last but not least is evaluation protocol, the way I mentioned. And I want to emphasize a particular area, which is evaluating creative writing, right? Language model, are they good to generate stories that are creative? are they good to evaluate, for example, writing, creative writing? And here's just a teaser. If you're interested, we had a paper at CHI last year. So we designed this theoretically grounded rubric to what is called Torrance test of creative writing. And this is in collaboration with experts in creative writing. They will have several dimensions: fluency, flexibility, originality, and elaboration. And then we compare the model output at that point in time. These were the state-of-the-art models, and then compare them with the experts. And we see that in a lot of areas, they are really not good. You have 2% rather than you have, the experts are actually much better. So we should be cautious about that. Again, here is an example of using them as assessor of creating tests, and the red part and also the orange means really disagreement or really slight agreement with experts. So really, they are not good at doing that. So what I propose and what we are working on is this human-centric approach, smaller model, human AI, and evaluation protocols. And what I will argue is that we want, besides the technological innovation, we want to be interdisciplinary. We want to involve the user who are using these technologies from the beginning. We want to do cross-sector, academia, industry, and then education, which means training the next generation of students and also educating the public on AI. And data science is the perfect way to do it because it really combines all of this. So with this, thank you to my PhD student, undergrads, masters, and all my collaborators.
All right. Thank you very much. So our third speaker today is Professor Matei Ciocarlie. He's an associate professor in mechanical engineering at Columbia University. As a roboticist developing intelligent systems for human environments, his work has focused on areas such as autonomous and human-in-the-loop robotic manipulation, assistive robots, and novel hand design and control. He focuses on reliable robotic performance in unstructured human environments and has developed new capabilities for mobile manipulators and made contributions to ROS, the open source robot operating system. Time magazine named his group's tactile robot hand the best invention of 2023. Professor Ciocarlie has a BS in computer engineering from the University Polytechnica of Bucharest and got his master's and PhD in computer science here at Columbia. Please join me in welcoming Professor Matei Ciocarlie.
All right. Thank you, Drumil. Good morning, everybody. So I'm a roboticist, and I'm here today to really tell you two things. The first one is that AGI is for real. That's what I believe. It's not around the corner, 6 months here. 6 months away, it's here. The reasoning capabilities of these systems are incredible. I think there's poetic beauty that they all emerge just from next token prediction in language, like Vishal was saying. But AGI is for real. That's number one. Number two, there's no guarantee, though, that it'll massively change the way we do things in the world. It'll boost our productivity, that it'll change our economy in huge ways. That's not guaranteed. And you might ask, wait a second, that doesn't track. You're saying it's incredible, it's AGI. How come it might not have such an impact? And, there are other people, more illustrious than me, making this argument. Nobel Prize-winning economist Paul Krugman draws a parallel to the internet. Drumil was talking about the internet in his intro. And oddly enough, if you're looking for that huge productivity boost that the internet created, you're not going to see it in the data. It's not there. And, technologies that are in the world of bits inside computers, sure, we can listen to music, we can stream movies, it's amazing. It doesn't necessarily make us more productive. So will AI go the same way, or are we going to have that actual boost in the physical world from the rise of artificial general intelligence? And the reason why that's harder than you might think is that in order to have that impact in the physical world, you need to make or move goods to have an impact in the economy in terms of productivity. You need to physically assist people who need help. Maybe in the services industry, maybe in healthcare. And for those things, abstract semantic intelligence, the way that these systems have, is not enough. You need the physical embodiment that allows you to effect change on the world. If you think about ourselves, right, we have our amazing abstract reasoning brains. We also have our hands, and these evolved together over millions and millions, hundreds of millions of years in synergy with each other. So, can we do something similar for AI, get it out of the virtual world and into the physical world, into the physical economy? And for that, we will need to provide it quite literally with hands, which is what my group works on. One example is that we are developing tactile robot hands. This is an example of a robot finger that we've built over a couple of years. This is a very close collaboration with Professor John Kimisis in the EE department in engineering. And this is how our tactile finger works. It's non-anthropomorphic in nature. It works based on light transport. Under the skin, our finger has lots and lots of LEDs and photodiodes, which are constantly talking to each other and giving us signals about what the finger is touching. And because of this, this finger is starting to approach the density of information that you have in your own fingers. Your fingertip has 500 to 1,000 individual mechanoreceptors. And this one is generating similar amounts of data. How do we process all that data with machine learning? It's a physical device designed from the ground up to be used in conjunction with machine learning. Here's our training data collection. Wait, no, this is actually prior work. This is not us. This precedes us by a little bit. I got the wrong video. This is our data collection. So we collect large amounts of training data so that we can train our own machine learning algorithms to make use of this very rich sensory stream that's coming from these new sensors that we're building. This is what the model looks like after it's been trained. We have this ability to localize touch very precisely over complex multi-curved surfaces, again, just like your own fingertip. And then we can train higher level models to do things like searching for buried objects inside granular media. This is using a technique called deep reinforcement learning, which is also used to fine-tune the performance of language models to make them more human-like in their interactions. So exactly the same methods are used here to train our robot to use the tactile data to search for buried objects. Or here, this is again deep reinforcement learning used to learn a very complex motor skill. In this case, dexterous manipulation based only on tactile and proprioceptive data. And we can be highly dexterous, more dexterous than we'd seen before. And because this only uses touch information and proprioception, we can do fun and slightly gratuitous things like, hey, look, we can manipulate in really difficult lighting conditions. Let me see vision people do this in these conditions. So what's happening next? What are we doing right now with these techniques? We're building always new robot hands. We're trying to deploy them for various tasks. We're looking to automate, to improve productivity in manufacturing, for example. This is a very important topic these days. We need a manufacturing boost. It's important to have short supply chains. We saw that after the pandemic, how critical it is to have short supply chains, to manufacture close to the customer. So we're looking at dexterous robotic manipulation applied, for example, in manufacturing, in building goods. But another line of work that we have looks not at robot hands, but specifically at human hands. This is a patient with a spinal cord injury wearing an exoskeleton that we built to help grasp objects. Here you see on the left is without the device. On the right is with the device that provides assistance for grasping. This is work done in collaboration with Dr. Joel Stein and Dawn Nilsson at the medical school at the Rehabilitation and Rehabilitation Medicine department. So this is for spinal cord injury. This is a version of our exoskeleton for stroke patients. And as unfortunately, I'm sure many people even in this audience know, stroke affects almost 1 million Americans every year. almost half of them don't get full use of the affected hand back. So here we're building exoskeletons to help people. In this case, for stroke, we're helping them open the hand, extend the fingers. And the interesting thing here is that our exoskeletons need to understand what the person is trying to do. They need to infer the intent of the human. And the way we do that is with electromyography. There's an EMG armband sitting on the person's forearm. We collect EMG data, and the interesting thing is that EMG, at the end of the day, is language. It's a language that your muscles speak, but it's still a kind of language. So it makes sense that we'll be able to use exactly the same tools in next token prediction that were developed for ChatGPT to use them to understand EMG data and understand what the person is trying to tell us via their muscle activity. And we call that Chat EMG, and we're using that to infer what the person's trying to do so we can provide assistance. This is a video that's 2 days old. This is unpublished work, but this is a person walking in, putting the armband on. The model, our model, has never seen this person before. Just like you ask ChatGPT a question, it's never seen your question before. But because it's been pre-trained on a large corpus of data and it uses these generative pre-training tools, it's able to adapt zero shot to this person just walking in and understand the language of their muscle activity and infer their intent. So to conclude, AGI is wondrous. Trust me on that. I'm sure many of you already believe that. Physical embodiment is going to be key to have an impact on the real world and on our society. Thankfully, a lot of the same tools that were developed for AGI can also help us build this physical embodiment and get these two talking to each other. So huge credit to everybody in the lab and our collaborators, and thank you for your attention.
Thank you. And the last stop on our whirlwind tour through the cutting edge of AI is David Sandalow, who is the inaugural fellow at Columbia's Center on Global Energy Policy and the co-director of the Energy and Environment Concentration at SIPA. He's the lead author of AI for Climate Change Mitigation Roadmap and the Guide to Chinese Climate Policy, and chairs the ICEF Innovation Roadmap Project. He's a former senior official at the White House, State Department, and U.S. Department of Energy, including roles as acting undersecretary and secretary for policy. He's the founder and director of the Center on Global Energy Policy's U.S.-China program and a visiting professor in the Schwarzman Scholars Program at Tsinghua University. He's also a distinguished research fellow at the Oxford Institute for Energy Studies and a distinguished non-resident fellow at the Atlantic Council. Sandalow is a graduate of Yale College, where he got a BA, and the University of Michigan's Law School. Please join me in welcoming David Sandalow.
Thanks, Ramil, and thanks to Garud and Alexis and the entire team that pulled together this impressive event. Can AI help us fight climate change? That's my topic today. And I'm going to go through a book-length report that a great team pulled together several months ago to help give a brief synopsis of some thoughts on that question. So here's the topic of our report: how can AI help reduce emissions of greenhouse gases? It has 17 chapters and 5 to 10 recommendations in each chapter. We wanted to be very clear about what different stakeholders could do, not just the analysis of the issue. And you can find it at these websites. Print version is available on Amazon. And we've recently launched the AI, Energy, and Climate podcast. So if you're interested in follow up on any of these issues, please go to, as they say, all your major podcast platforms. It has the AI, Energy, and Climate podcast where we talk about these issues in some depth. Interesting. There it is. So our book has 17 chapters. We look at 8 different sectors: the power grid, food system, and more. As you can see here, a variety of cross-cutting issues, 334 pages total. And there's a lot of detail in those 334 pages, so just here are 5 key takeaways from our report. The first is that AI has significant potential to help fight climate change. we break it into two categories: incremental gains and transformational gains. Examples of incremental gains are, for example, improving the productivity at solar farms. That's happening right now with better weather data from predictive models. You can do better tracking with panels, and same thing with wind turbines, and improve the productivity at renewable generation farms. There's also transformational gains, and I'll talk about these in a few moments. We also looked at how much greenhouse gas emissions are contributing or increasing as a result of AI. And I find this is what gets the most conversation in the public dialogue. There's a lot of focus on the energy use from data centers and the potential increase in greenhouse gases from that. If we dig into the data, which I did pretty deeply over the course of the past year, we find that today probably greenhouse gas emissions from data centers are less than 1% of the global total, but that's very likely an increase in the near future as a result of the rapid energy demand for AI. The main barriers to realizing AI's potential to fight climate change is the lack of data and the lack of trained personnel. Trust in AI is essential. Unless AI is trusted, people aren't going to deploy it in order to the many ways that it can fight climate change. And then we recommend that every organization with a role in climate change mitigation should consider opportunities for AI to contribute to its work. So we actually start with 2 chapters of background, one chapter of background on Introduction to AI, and another on Introduction to Climate Change. I don't think this group needs an introduction to AI. This chapter was written by my colleague Alp Kuchu-Kelbier, who teaches at CS, and we're teaching a course together at SIPA. But I thought you might be interested in a way that we talk about AI's capabilities to lay audiences. And what we say, we summarize AI's capabilities in 4 ways. AI can detect, predict, optimize, or simulate. And then we offer examples of each of those in the climate change world. For example, AI can detect methane emissions from satellite data. It's a very important application of AI, which has actually been transformational in our understanding of methane emissions, which is the second most important greenhouse gas. Can predict weather patterns at solar wind farms. I've spoken about that. Can optimize power flows on transmission lines, makes a big difference, and then simulate battery chemistry reactions. On an introduction to climate change, for those who aren't familiar with this topic, we have a great chapter that's written by actually the chair of the Intergovernmental Panel on Climate Change, which is a great honor for us to have him write this chapter. But just a few statistics for those who aren't familiar with the climate change topic overall. Atmospheric concentrations of heat-trapping gases in the atmosphere are now higher than at any time in human history. And July 22nd, 2024 was the warmest day ever recorded. 2024 was the warmest year ever recorded by far, and one day, 1 year doesn't make a trend, but the warmest 11 years ever recorded were the last 11 years. So we have 8 sectors in the book. I'm only going to talk about one of them here because for lack of time, but which is the food system. And I find many people are not aware that the food system actually contributes 30% of global greenhouse gas emissions. In one way, that's not surprising since everybody on the planet almost eats food every day. A lot of our infrastructure relates to the production, cooking, disposal of food. And of course, then climate change threatens the food system. So the causality goes both ways. And AI can contribute to more sustainable food systems in a variety of ways. We go through them in the book. Integrating data from soil sensors and satellites to create better fertilizer management plans. Fertilizer releases nitrous oxide into the atmosphere, which is a greenhouse gas. Creating virtual farms can help in simulating different conditions. The barriers include lack of data, especially in the global south. And then there are real risks here, both in terms of increasing inequality and then kind of myopic optimization. If you've got an AI tool that focuses very much on short-term yield from a farm, you may have degradation in terms of the long-term productivity of that farm. So you need to be sure that the AI is optimizing for the right outputs. One of the areas I'm most excited about in the climate change world when it comes to the use of AI is materials innovation. New materials are vital for low carbon technologies. I remember I worked at the U.S. Department of Energy years ago, and I remember when I got there about 15 years ago, the career staff there telling me that offshore wind would never really work. And the reason they thought offshore wind would never really work is because the marine environment is too corrosive, and you could never really put turbines large enough out in the marine environment. Well, innovation in materials has helped us conquer that problem. And there's lots of areas, including battery chemistry and lightweight materials for vehicles, where materials innovation could be transformational when it comes to the fight against climate change. And of course, the way materials innovation was done historically is by Thomas Edison's example up in the upper right-hand corner. When he created the modern light bulb 150 years ago, he kind of famously spent a year physically trying different materials over and over again, running electricity through them to see how much light and heat would be produced. Today, we can simulate, 1 million of those types of interactions in a second, rapidly accelerating the pace of innovation. And there's already a lot of good work in this area. AI tools are being used to summarize the vast literature on particular chemicals, search millions of possible materials, identifying materials for physical testing. And actually, one of the particular benefits of AI tools here is that we're not limited to materials that physically exist in the world right now. We can simulate different materials, and then if it looks like they're promising for the characteristics that we are searching for, synthesize them and see if they work. So I think this is a very exciting area. We have a number of recommendations in the report. We actually have more than 100 recommendations in the report, but just to pick out a few, we recommend that governments, businesses, and philanthropies create fora in which AI experts and climate change experts come together. In my experience, that's one of the most important things. We have a lot of AI experts who might be interested in helping out climate change, but don't know a lot about the topic. And we have a lot of climate change experts who would like to use AI tools, but don't know much about the topic. So thank you for this forum in which you're bringing a climate change expert to talk to a group of AI experts. We recommend governments assist in sharing data and others, which I don't have time to run through since I'm running out of time. But just to summarize, here's our topic. Here's where you can find copies of our book. And if you're interested, please listen to the AI, Energy, and Climate Change podcast. Thanks a lot.
Okay, thank you very much. So I think we have a few minutes for questions. I'll start with Vishal. Do you agree with Matei? Is AGI here? What is AGI? We keep hearing about it.
So it depends on what you mean by AGI. If you mean a completely advanced general intelligence that matches human intelligence, no. It's not here, and the LLMs cannot possibly scale to that. But is it extremely useful that it feels human-like? Yes. I'll tell you a secret. I mean, my entire talk, I created that using LaTeX, but I did not type in the commands. I interacted with an LLM. I said, I want this on this slide, make this figure, change it this way. The entire talk was generated using LLMs. And so I had an incredible assistant, which is almost like AGI, but it's not AGI. So I think for a long time, the human would be required in the loop. It's not an independent, autonomous, entity that will take over the world, but it's incredibly powerful.
So Matei, what did you mean when you said AGI is here?
So I meant that it deals in abstract concepts in a way that until 2 or 3 years ago, I would have thought impossible. And that for me was the aha moment when I realized that in the process of processing all of those tokens that Vishal was talking about in his talk, and in taking that matrix and distilling it into a model, probably the system has no choice but in its latent space to identify abstract concepts and to deal in abstract concepts. And when I realized that a model trained exclusively on text, that has only ever seen text, for some reason has spatial reasoning capabilities and visual reasoning capabilities. If you take a model that's only ever seen text, you describe to it the layout of a house, and then you ask it to generate text that compiles into an SVG graphic of a map, it does it, which to me is nuts. So it doesn't have to be like human intelligence. It's not completely similar. Our intelligence evolved with other constraints. We had to survive, and we had to get food, and we had to reproduce. So our intelligence, of course, is going to be somewhat different, But in terms of the abstract reasoning, I think it does many, many things just as well as we do. And to me, that is incredible.
So, Smaranda, it seems like both in Matei's work, your work, sort of everything we've heard, there's this tension between general and specific, right? Like we're building these things, you want to build sort of culturally competent models, that is a sort of generalizable problem, but then you also want to do very specific things for social good, like applications to public health or writing, or in Matei's case, make the robot screw in the nut, right? And so we have this tension between general and specific. How do you think about balancing those in your work, and especially as we think about aligning these to human values?
Yeah, that's a good question. And I think in some of the approaches that we are looking at is, of course, we're going to rely on some of these kind of general large language models, but then we actually adapt them to the specific problem we are trying to solve. Especially we want to focus on the smaller model using domain knowledge. So for example, using domain from the health domain or from cultural norms and then specializing them for the task that you want to do. So I would argue more towards like starting with the general, but adapting to the problem you are trying to solve, using insights, let's say, from a theoretical domain you are trying to apply it to. So I would do it more on kind of generalizing specialized models for the problem, when you're having the human in the loop as well.
And you talked a little bit about small models, like using small models for specific problems. Can you tell us a bit more about that? And also, Matei, I'm curious if there's like an analog to that in the mechanical world.
Right. So what we're seeing here is more kind of, if you have this very, very large language model, like billion, trillions of parameters and so on. So kind of looking on the smaller models that you can, for example, run them on fewer GPUs or on your laptop, going towards, let's say, edge devices and things like that. I think that's what I would see.
So the idea is not to use a sort of mallet to nail in a small nail. You want a smaller hammer to nail in that. Is there some kind of analog in your world, Matei?
Absolutely. And it's interesting because we're seeing it literally happening right now. In the last maybe 4 weeks, we've seen a couple of releases. Google released Gemini Robotics. Figure AI released Helix, and NVIDIA released Groot just, I think, a week ago. All of these are large models for robotics, and all of them follow the same pattern in that there is a big model that does the slow, abstract semantic reasoning that's probably running in the cloud. And then there has to be a second model, much smaller, which is running on the robot. It has to be small because it has to run on embedded hardware that operates fast and does the motor control, the low-level reasoning. And that beautifully mirrors this idea of system one, system two thinking that people believe happens in our brain as well. If you've read, for example, Daniel Kahneman's famous book, Thinking Fast, Thinking Slow, this is exactly what we're seeing now in these large models for robotics. And I think there's a beautiful, beautiful symmetry there.
So, and I'm also finding in my work, I'm also using sort of large models for prototyping, figuring out what is possible. Once I know what I want to do, I try to transition to a smaller model to sort of reduce the environmental impact, right? So do I really need to burn that much energy to do this one task over and over and over and over again? Maybe not. So David, the last question is for you. We talked a little bit about the amount of energy used for these AI models, and obviously we can do what we can to minimize, not use the large models for the smaller tasks and sort of minimize the footprint as we go along. But as you mentioned, there are maybe more gains in proactively using AI to sort of reduce the environmental footprint. But what do you think is the on balance here? What do you think AI will do to the environment? Because on the one hand, it consumes resources. On the other hand, it can be used to save resources. So where do you think that the net balance will be here?
So I've studied this very closely in the past year, and I actually have a very confident answer to this question, which is nobody knows. Both scenarios are possible. I think it is absolutely possible that the negative environmental impacts of AI will be greater than the positive ones for the reasons you were pointing to. And I mentioned briefly in my talk, AI is going to consume lots of energy in the years ahead. If we use carbon-based fuels in order to power data centers, that's going to have big impacts on climate change. There's also water impacts, which are a concern. So the negative impacts could be big. But for all the reasons I was pointing to in my talk, the potential for AI to make improvements when it comes to all these issues is enormous as well. So I think the real question is, how do we maximize the likelihood that AI is going to have a positive environmental impact? And I think one of the keys for that is getting communities who know a lot about AI together with communities who know a lot about climate change and clean energy applications, so they can cross-fertilize ideas and work together on this problem in the years ahead.
Great. Well, friends, I think it's up to us to figure it out. Thank you very much, everyone, for this stimulating conversation.